This video is about learning outcome 1, which is all about computing measures of variation, including the range, standard deviation, and variance. And then we're also going to discuss the properties of these measures of variation. So here's our list. The range is the difference between the maximum value and the minimum value on our data list. So that's one measure of variation. The second measure of variation is standard deviation. This is a measure of how much data values deviate away from the mean. And then lastly, we have variance, which is just that standard deviation squared. And we're going to use the following round-off rule for measures of variation. We want to carry one more decimal place than is present in the original data set. So let's look at the first measure. The first measure is range. Range is the difference between the maximum value on the list and the minimum value on your list of data. So let's look at properties of the range now. Range is very sensitive to outliers, which makes sense. If you have a maximum value or a minimum value in there in your formula, and the formula is based only on these two values, if you have an outlier, it's going to be a max or a min. Or, you know, if there is an outlier, one of them will be a max and one of them will be a max or a min. So this is very sensitive to outliers. So this is not a resistant measure of center, or excuse me, measure of variation. Now, range does not take every data value into account. It's just using that max and min value. So we might say that it doesn't reflect the variation among all of the data values in the way that we would like it to. We'd really like to see how all of the data values vary together, measured by a single number. And the range doesn't tell us that. The range just says, like what is the range of values that our data spans over. It starts here and it ends here. When I think of a range, it makes sense that we're saying, well, how big is it? What's the max value and the min value, and how large is that interval? Well, that doesn't take into account the variation in between. So that is one downside of range. One plus side of range is that it's very easy to calculate the max and the min, or the difference between the max and the min. You just sort the data, you find the max and the min, and you subtract. So that's a very nice property of range. So let's look at computing the range. We're asked to find the range of these Verizon data speeds in megabits per second. They are 38.5, 55.6, 22.4, 14.1, and 23.1. So if I want the range, I need to find the max, which is that 55.6 megabits per second. And then we look at the min, which is 14.1 megabits per second. You just subtract those, and so the range is 41.5 megabits per second. Now our second measure of variation is the standard deviation, and we're going to focus here on the standard deviation of a sample. This is denoted by S, and it's a measure of how much data values deviate away from the mean. So the notation we'll use is this. S, lowercase s, is for sample standard deviation. And this little, it looks like an O with a little tail on it at the top. That is a lowercase sigma, and that represents the population standard deviation. The sample standard deviation can be calculated using this formula. And from this you can see, this is really the definition of a sample standard deviation. You can see what we mean. You can see what we mean because it has a mean in it. Bump, it's getting late. What we're doing is we're measuring deviation from the mean. So we take all of the data values on our list and we subtract them. And we're trying to get a sense of that deviation from the mean. But if we subtract them and we don't do anything to those numbers, it's not going to give us, it's going to give us a positive number when the data value is above the mean, and it's going to give us a negative number when the data value is below the mean. And if we were to add all of those together to try to measure the deviations, the negative values and those differences and the positive values and those differences, they would all cancel each other out just by the very nature of the mean itself, they would all cancel each other out. So we need to do something else if we want to measure deviation and we want any deviation from the mean to be considered positive. So this is what we do. We subtract that mean from the data value, so that's giving us a deviation from the mean, and then we square it. And we do this for all of those values, and we add them together, and we divide by the sample size minus 1. And then to undo that squaring, in some sense, we're going to take the square root of the answer. And that's going to give us the sample standard deviation. Now, in practice, that's actually pretty difficult to calculate. So we're going to use this formula instead. This formula is also used by calculators and software. It looks more complicated, but it's actually much easier to use than that first formula. There's a lot more work that goes into that first formula, as we'll see when we do an example. Now, for the most part, when we find sample standard deviation, we're not going to use either of these formulas. We're going to use software. We're going to use something like Excel or a calculator to calculate the sample standard deviation. But it's important that we do some hand calculations just so that we know what the calculators and the software are doing. And then it's really important that we understand this first formula, that what we're actually measuring is that deviation of the values from the mean. And this first version of the formula, even though it's more difficult to use, really illustrates that, because you take the deviations, you square them, you add them together, and then this act of squaring them and then taking the square root, they almost undo each other, but not quite, because you're adding them together before you take this. You're adding them together and then dividing by n-1 before you take the square root. But that's giving us some measure of how much those values deviate from the mean, and it's treating all the deviations as positive, whether that x value is below the mean or above the mean. So let's actually use one of those formulas. Before we do that, we are going to look at 7 important properties of the sample standard deviation. Remember, this is a measure of how much data values deviate from the mean, and we treat all deviations from the mean as positive because we square them first before we add them together. Now, because you're taking all those values, those deviations, you're squaring them, adding them together, dividing by a positive number, and taking the square root, the sample standard deviation is always greater than or equal to 0. If you square numbers, you're always going to get something that's non-negative back. Now, here's another important property. I love this one because it makes a lot of sense intuitively. The sample standard deviation is 0 only when all of the data values are exactly the same. And that makes sense if you're talking about a measure of variation. If all of the data values are exactly the same, they're not varying. The variation is 0. And also, if you think about the definition, if all the data values are exactly the same, like, well, what's the average of 5 100s? Well, your average would be 100 if you got 5 100s. Of course, I'm using average in the way that Mr. Triola doesn't like, but you get the idea. If you have a bunch of values that are all identical, the mean is the same as the value itself. So when you start taking each of those values, which are equal to the mean, and subtracting the mean, of course, there's no deviation there. There's no variance, or not variance. We'll talk about variance in a little bit. There's no variation there. So it makes sense that this measure of variation is 0 when there is no variation. The next property is that larger values of the sample standard deviation means that there's more variation in the data. Now, this is very sensitive to outliers. You put some outliers in your set, and then you subtract the mean, and then you square it. Well, that's going to make a big difference in that numerator for that expression on the other page, or on the other slide, excuse me. So this is not resistant. If you've got different samples, and some of those samples have outliers, they're going to have different sample standard deviations. The outliers will make a big difference. Now, if you take the original units, you take the original values, that let's say that they're in minutes, and you subtract the mean, which is also in minutes, and you square it. It's going to give you minutes squared. You divide by a constant, still minutes squared. Or you add them all together and then divide by a constant, you're still in minutes squared. Then you take the square root, you get the minutes back. Because we squared something and then we took the square root, we're going to have the exact same units that the original data values have. That makes it easy to interpret sample standard deviation. So if the original data values are in minutes, the sample standard deviation is in minutes. And it's very helpful because when you think of quantities, if you're talking about this number plus or minus, or this many minutes plus or minus this many minutes, like that makes a lot of sense to us. We can think about that variation in that way. So sample standard deviation is easy to interpret because it has the same units as the original data values. Now, the last quality of sample standard deviation is that it's a biased estimator of the population standard deviation, sigma. And I'm going to tell you what a biased estimator is on the next slide. So this is just the basic difference. We're going to revisit this idea in the next learning outcome for this lesson, and then also again when we talk about sampling distributions in Chapter 7. But the sample standard deviation, S, we say it's a biased estimator of the population standard deviation, sigma. And this is how you want to think about it, excuse me. The sample standard deviation, we're using that as an estimate of the population standard deviation. So we don't have all the values for the population. If we did, we could just calculate the sample or the population standard deviation and there would be no need for the sample. But we don't want to do that. We would like to take some subset of the population, hopefully randomly selected, and then calculate a sample standard deviation and use that to estimate the population standard deviation. But the problem is it's biased, and this is what we mean by biased. The values of the sample standard deviation do not center around the population standard deviation. We're going to talk more about this later, but the idea is if, let's say, our sample had 100 elements in it and the population was much, much larger than 100, if you take 100, you randomly select 100 pieces of data from the population, and then you calculate the sample standard deviation, and then you put them all back, and then you do it again, 100 different data values, and you calculate the sample standard deviation, and you do it again, and you keep doing it in this way. And you're going to have all these different sample standard deviations. Our hope is that if this is a good estimator of the population standard deviation, that the mean of those, if I took all those sample standard deviations and I looked at them, let's say on average, I hope that they look like the population standard deviation, but they don't. That's why we call it a biased estimator. We would prefer to have an unbiased estimator so that as we continue to sample from our population and compute standard deviations, like they would sort of group around the actual value that we're trying to estimate. That's not what happens here. So the sample standard deviation is a biased estimator of the population standard deviation. So in this slide, we're looking at an example. We're asked to use the sample standard deviation formula to find the standard deviation of these data speeds. In order to do this, I'm going to share my paper with you. Let's see. And we're going to use that formula that is based on that definition. So I'm computing a deviation of that value, each data value from the mean. Then I take those deviations and I square them. I divide by 1 minus the sample size, or excuse me, the sample size minus 1, and then I take the square root of the answer. I want to compute this for my small data set. And in order to do that, I'm going to list my X values in a column right here. I had 38.5, 55.6, 22.4, 14.1, and 23.1. Now we want to use this formula. So the next thing that I need in order to use the formula is my mean. Now in order to find my mean, my sample mean, that's x bar, I've got to add up all the x values and divide by the sample size. We can all see that the sample size is 5. So I'm going to add these x values now. This is actually really easy to do in Excel. And you'll see me doing that in Excel in some of the videos. So I get 130.6 as the sum of the x's. Now I need to compute x bar, that's my sample mean. So I take 130.6 and I divide by the sample size, which is 5. And I get 26.12. I feel like I got different values last time I tried this. 153.7. I don't know how I messed that up. I must have missed a number. So 153.7 divided by 5. There we go, 30.74. That's what I remember when I did this before. So now we want to take each of these guys and we want to subtract the mean. So that's giving us the deviation of this particular value from the mean. Okay, so now we are going to take 38.5 and subtract the mean. So I get 7.76, and we're just going to keep going like this. $55.6 minus the mean. We've got 22.4 minus the mean. $14.1 minus the mean. And then 23.1 minus the mean. Okay, so now we're going to take all of those values and we're going to square them. Because if I were to add all these deviations together right now, you can bet you're just going to get 0. See, that one's like negative 7.7 and that one's close. This is kind of like negative 24 and that's positive 24. They all cancel out. So if I were to add the deviations now, I get 0 just because of the nature of the mean. So we need to make those positive so that the negatives and the positives don't cancel. That's why we square them here and then we take the square root later. So let's square them. I'm doing all this on my calculator over here. Again, this is easier in Excel. And a negative number squared is the same as that same number positive and squared, because a negative times a negative is a positive. Okay, so that's x minus x bar, so it's each value minus the mean squared. And now we want to add all of those up. So we've got 60.2176 plus 618.0196 plus 69.5556 plus 276 58.8896 plus 58.3696 equals the sum of x minus x bar squared is 1083.052. I want to take that and I want to divide by 1 minus the sample size. Sample size is 5, so we'll divide by 4 and then take the square root. And I get about 16.45. And this goes out to 1 decimal place. When we're computing sample standard deviation, we want to go out 1 more decimal place. So we want to go to 2 decimal places. All right, so let's go back to our PowerPoint. And we see we get exactly the same thing. So they have the mean of 30.7, which is what I got. I got 30.74. And then they took the x's and they subtracted the means, they squared them and added them together, and they got this 1083.052, which is what I got right here. And then n minus 1, if n is 5, n minus 1 is 4. And then you just substitute everything into the formula, and you get that 16.45 megabits per second. Okay, so that is the first formula, and the benefit of using this first formula, again, is that you've got that x minus x bar in it. So it's showing you that deviation, and then we square it to make all the deviations positive, and then we later take the square root to sort of take care of the units. Notice the original units were in megabits per second, and now the final units are in megabits per second. Okay, now we want to use the shortcut formula instead. The shortcut formula does not look like a shortcut, but it's actually a shortcut. I know it's surprising, but this is actually easier to evaluate than that first one. Okay, so we're using exactly the same data set. I will share my paper with you again. So this time, in order to use this formula, you want to be very careful. You've got the sum of the x's squared here, and then you've got the sum of the x's squared. So we don't need to compute this x minus x bar squared the way we did here. We don't have to find the mean, then do the subtraction, then square them, then add them. Instead, all we have to do is add up all the x's, which we've already done. We got that 153.7. And then we want all of the x's squared in this column. We want to add those up as well. So we had 38.5, 55.6, 22.4, 14.1, 23.1. And we want to take each of those numbers and square them. So 38.5 squared, 55.6 squared, 22.4 squared, 14.1 squared, and 23.1 squared. And then I add those up to get the sum of the x's squared. So I've got that 533.61 plus 198.81 plus 501.76 plus 3091.36 plus 1482.25. There we go. So I've got 5,807 and 79.79. Okay, and then the sum of the x's, which we did earlier, was that 153.7. So that's all we had to do, is we just squared those and then we add them together. And then we substitute into our formula. Sample size is 5. You multiply by the sum of the x's squared, so that's this number. And then you subtract the sum of the x's, that's 153.7 squared, and you divide by the sample size. Times 1 less than the sample size. So I'm going to focus on that numerator first. So I compute that. And then I'll divide that by either 20 or open parentheses 5 times 4. Make sure you have those parentheses there if you're not going to do the arithmetic in your head. Otherwise, it'll divide the result by 5 and then take the answer of that and multiply by 4. We want the 5 and the 4 in the denominator, so we need the parentheses. Okay, that's this expression. Take the square root of that. And we get that 16.45 megabits per second again. So that's good. We get exactly the same answer either way. And that's exactly what we want. So this actually, I hope you can see that this is much simpler, even though the formula itself looks longer and more complicated. It's really not. Okay, now in this slide, I'm just showing you some formulas. You have a homework problem where you do this, and I have made a video demonstrating how to do this for a particular homework problem. But I just wanted to put this in the slides so that you know what's coming. Sometimes, rather than giving you the data set, they give you a summary of the data in the form of a frequency table, a frequency table, which is the same as a frequency distribution. And what we'd like to do is approximate the sample standard deviation given the frequency distribution. So here is the shortcut formula that we just used. The sample standard deviation is the square root of the sample size times the sum of the x's squared minus the sum of the x's, quantity squared, all of that divided by the sample size times the sample size minus 1. That's true if you have all the data. Now, if you don't have the data, but you just have a frequency distribution instead, you can use this formula instead. Now, these x's are different than these x's. Since we don't have the data values, we can't use the top formula. But what we can do is we can say, okay, if I've got a class and I know that there are this many elements in it, let's say that there are 11 elements in that class. I don't know what the values are in that class, but I can approximate them all by the midpoint. I can say, I bet they're about this much. Well, if I take that class midpoint and I multiply by the frequency, it's like let's say there were 11 of those, it's like adding that number, that class midpoint to itself 11 times. And that's going to be an estimate of the sum of the values in that class. If you do that in all of the different classes, you get a sum of the frequencies times the class midpoints, which is an approximation of the sum of all the x values here. You can do the same thing for the sum of the x's squared. We don't actually know what all the values are. So what we can do is we can find that class midpoint, and we can square it and say that's approximately equal to the squared value of one of the values in that class. And then if I want the sum of all the squared values in that class, I multiply that class midpoint squared by the frequency. And it's almost like adding up all of the x squareds in that class. And you do that for the next class and the next class and the next class. You do that for all the classes. And that's going to give you an approximation of the sum of all of the x values in the original data set squared. So you're just replacing this piece with this piece and this piece with this piece, and it makes sense. And that's going to give you an approximation of the sample standard deviation. So check out those videos. It's on the Statistics Homework Help playlist on YouTube, and it's also on Blackboard, embedded in our course site. So you can watch that video if you want to see somebody work that out before you attempt the problems on your own. Now, we've been talking about sample standard deviation. The standard deviation of a population is a little bit different. So instead of using the n-1, that sample size minus 1, like we do for a sample, when we're calculating the population standard deviation represented by sigma, we use the entire population size n, not one less than the sample size, but the whole sample or the whole population whenever we calculate that population standard deviation. So you take your x values And now you've got all of them. You don't just have a sample of them, but you have all of them. You subtract the true value of the mean. So that's giving you a deviation from the mean. You square those to make all those differences positive. And then you divide by the population size, capital N. And then to undo that squaring, in some sense, we're taking the square root. And that will give you the original units back. So we use capital N here, which is the size of the entire population. But with the sample standard deviation, this is when we're dealing with a subset of the entire population and not the whole population, we use the n minus 1 in the denominator. Now the variance of a sample is denoted by s squared, and that's just the sample standard deviation squared. So we'll have s squared for the sample variance, and if we use sigma squared, we are referring to the population variance. So that first important property is that it's the definition. Sample variance is just the sample standard deviation squared. Of course, any number squared is going to be greater than or equal to 0. And then just like before, the standard deviation is 0 when only when the values are all exactly the same, because there is no variance. There is no variation, excuse me, if all the values are exactly the same. So if I take that sample standard deviation and I square it to get the sample variance, well, the only time I'll get 0 from that is when all of the values are exactly the same. So this is a good thing. It means that if we're trying to measure variation, we're getting a 0 for this measure of variation when there's no variation at all, when all the values are the same. So that's exactly what we would hope and expect for a measure of variation, and that works out. It's measuring it the way we would hope that it would measure. The sample variance is very sensitive to outliers. If you take an x value and you subtract the mean, if that x value is far above the mean or far below the mean because it's an outlier, well, if you take that value and that difference and you square it, it's going to be very different. It's going to be a very different sample standard deviation than you would get if that outlier was not in your sample. So this is not very resistant. Now its units, since we're squaring that sample standard deviation, the units of the sample variance are not the same as the units of the original data set. They're the squared units of the original data values. So if your original data values were in minutes, your sample variance will be in minutes squared. This makes it a little bit harder to interpret, like what is a squared minute? So it makes it more difficult to interpret than the standard deviation. For that reason, we're going to tend to rely more on standard deviation, even though sample variance is got a lot of great properties, and one of them is this. Sample variance is an unbiased estimator of the population variance, sigma squared, whereas the sample standard deviation, if you kept creating new samples all of the same size and you kept calculating standard deviations for all of those samples, they would all not be targeting the value that you're going for. Well, that doesn't happen with the sample variance. If you calculate the sample variance a number of times after calculating a bunch of different, or after collecting a bunch of different samples from the same population, and then you calculate the variance and you calculate the variance and you calculate the variance over and over again, and then you look at the mean of all those sample variances, it turns out that they get close to that population variance. They target that population variance. We're going to talk more about unbiased estimators in the next video, biased and unbiased estimators. So in this one, we're asked to calculate the sample variance. It says, find the sample variance of the Verizon data speeds. It's the same data speeds from before. And we've already got the sample standard deviation. Well, then it's really easy. If you want the variance and you have the standard deviation, all you have to do is square it. And so we end up with 270.6 megabits per second squared. Again, this is a little bit more difficult to interpret than this, but that's the variance. And another, the benefit of using the variance as opposed to the sample standard deviation is that it's an unbiased estimator, whereas the standard deviation is a biased estimator of the true population parameter that we're interested in. Okay, so this is our notation summary. Whenever you see S and S squared, those are referring to the sample. S is that sample standard deviation. A benefit of it is that it has the same units as the units of your original data values, and that means it's really easy to interpret. But it is a biased estimator of the population standard deviation. Sample variance is the S squared. It's an unbiased estimator. If you keep taking different samples and you keep computing the sample variance, it's going to, all of those are going to tend towards the population variance. So it's targeting what we want. If we're using these as an estimate for these, the S squared is truly estimating this thing that we're looking for. Apparently S isn't, so that's a problem. But the downside for using sample variance is that it's got units that are not the original units of your data set, but it's got those units squared, which makes it a little bit less easy to interpret. So that's it for our measures of variation. We had the range, that was the max minus the min. We had the sample standard deviation, and we've got two formulas for that. I showed you how to use both of them. The second one is easier to use. And then we looked at the variance, which is just the sample standard deviation squared. Now we're going to emphasize interpreting all of these values a lot in the other videos. In this video, we were just focused on computing those values, but there will be more about interpretation in the videos to come, so make sure you watch the videos to come.